Okay, the nice part about the using Excel or MATLAB or R is when things get big. So this nasty equation over here, this 5 by 5 covariance matrix. So we have the coefficients multiplying the x's right here, the 1, the 1, the 1. And we have the coefficients. For the first row there. And for the third row, we get the 3, 7, and 4. And then we have the B over here. All right, so what we did, this is the matrix multiplying the A inverse, or I guess I call it C in this case, matrix C inverse times B. And that will give me my vector of x's. Right, so it works in Excel using that. And in R, I entered the matrix, put in the coefficients. R is kind of good because it sees the comma here and knows not to return, so it's waiting for new information. So I input the data, I give the number of rows, and I put by row. So as the numbers are red, it's going to be red across the row, first row, second row, third row. So I got my right C matrix. I create my B as B's 0, 1, 40, 25 over here. And what do? I just matrix multiply. So I take in R, this is C inverse times B, and that gives me my vector of x's. So yay, it works. All right, so let's talk about some special matrices. All right, so if we have orthogonal vectors, what these are is if we multiply them together, like A transpose B. So what do we have? Negative 4 plus 4 is 0. Right, so if we look at what these vectors are, what these vectors are directions. I can draw this better. Going out from 0. So it's an array going from 0. So we have maybe the x1 and the x2. So we can say that x1 is 2, x2 is 4. So what do we have here? So we go out 2 and go up 1, 2, 3, 4. So a vector is a direction and a magnitude. All right, so the magnitude is the length of this line, and the direction is a slope of 2 coming out of the origin. All right, so if we look at this second one, we have x1 is negative 2, x2 is 1. So we go back, negative 2, go down 1. So what do we have? So we go out to go down 1, or go up 1, I'm sorry. Go back 2, go up 1. And wow, I'm a terrible drawer. But if I drew this better, what we have right here is a right angle. So this is 90 degrees. So when we talk about orthogonal, what we're saying is that the rays are at 90 degrees to each other. So that in statistics, when things are orthogonal, they're unrelated. So they are in different dimensions or complementary dimensions. So we'll use some orthogonality conditions a little bit later. But anyway, that's what an orthogonal vector is, and or a matrix. And so when we look at a symmetric square matrix is one where if you take the transpose of the original, it equals the original. So let's say we have a covariance matrix. So we have the covariance of 1 and 2, 1 and 3, 1 and 2, and 1 and 3. It doesn't matter what the order is, but what we see is the first row equals the first column, the second row equals the second column, and the third row equals the third column. So when we swap the columns and rows, hey, it's the same damn thing. All right, so the symmetric matrices are, if we take the transpose, we don't have to worry about swapping anything out. Okay, that's it. I guess one thing we should talk about when we're talking about transposes, so if we have the, let's say A times B. So A is a 3 by 2, and B is a 2 by 4. So what we end up with is a C. So these things equal. C is going to be a 3 by 4 matrix. All right, so what happens if we take the transpose of C? Well, what we're going to have is that's going to be equal to the transpose of A times B. And so C transpose is going to be, well, the transpose of this. But what we do is we reverse the order and take the transposes of the items inside the parentheses. So this will be B transpose, A transpose. So the transpose of a 3 by 4 is going to be a 4 by 3. This transpose of B is going to be a 4 by 2. The transpose of A is going to be a 2 by 3. So it ends up being a 4 by 3. So anyway, that's when we take the transpose of a product, it is the reverse order product of the transposes. All right, so a diagonal matrix is one where the items in all the off diagonals, the diagonal is the row 1, column 1, row 2, column 2, row 3, column 3, etc., and all the off diagonals are 0. So I guess one cool thing about a diagonal matrix, 5002, if we take the inverse of this, it's just going to be 1/5, 0, 0, 1/2. So for the case where all the diagonals are 0, the inverse of a diagonal is just going to be the inverse element by element. A singular matrix is referred to, well, it is a non-invertible matrix. All right, so what we have is at least one row or column is a linear combination of other rows or columns. All right, so what this means is that we have a situation where we have some parallel lines or some equivalent lines equivalent to what we have with the problems up here. All right, so in any case, when we have a non-singular line, it's a case where somewhere within our information set, we have either some parallel lines or parallel dimensions or basically identical dimensions. All right, and so in this case, we don't have enough unique information. We need enough equations with coefficients that aren't related to any other coefficients. Or sorry, coefficients that are unrelated to the coefficients of any other lines or columns. All right, so let's see what we have here. I'm going back. Let's go to Excel and back up to here. So let's say we have the first row is 2 and 4, and the second row is 3 and 6. All right, so before I hit enter, what we're going to see is the second column is twice the first column. That's certainly a linear combination. And what happens? Hey, the A inverse no longer exists, and we have no answer. All right, so basically what this turns out to be is we are kind of dividing through by 0. So let's say instead of 6, all right, we're going to put in a 5.9. Right, so that is not a true linear combination, but look how big the answers are. So before, if this is a 5, well, basically this is a 0 and a 3, right? But if I change this to 5.9, this becomes a 40, a negative 54 and a 30. And if I change this to a 5.999, well, look at how this explodes. So as a matrix becomes closer and closer to being singular, as columns become very, very close to being linear combinations of others, we have some results that end up being explosive. So we'll see this in portfolio management. If we have nearly non-singular covariance matrices, we're going to get wild weights that are going to be plus or minus negative 1,000%. All right, so goofy things can happen when we approach the case where we have some singular matrices. All right, so we can determine whether a matrix is singular or not by looking at its determinant. So the determinant is, I guess there's some other uses for it, but it is a way of determining whether some lines or columns are linear combinations of each other. All right, so the rule is if the determinant, which we can write as either det A or the absolute value signs, it's the determinant of A. If it equals 0, we cannot invert. There is one or more redundant equations in there. All right, so we can have fun with finding determinants of 2 by 2s is really easy. So if we start back with our first equation, so we have first set of equations, 2, 3, 3, 4. Here's our A, and then we have our x variable, and we have the B, which is 12 and 15. All right, so to find the determinant of A, all we do is we take the product of the diagonals minus the product of the off diagonals. All right, so it'll be 2 times 4 minus 3 times 3. And so 2 times 4 minus 3 times 3, and that's going to be a negative 1. So the fact, I can write that better, the fact that this is not equal to 0 means we can invert this. All right, so what does this actually mean? So let's say if we had the case where we have 2 and 4 and 3 and 6. All right, so if we multiply the 2 and the 6, so what are we going to have? Well, I guess one thing we can do, we're going to get 12 minus 12 equals 0, and we can't invert this. So I guess what this says is if we multiply the first, so if we have 2x plus 4y, if we equals, I don't know what, 2x plus 4y, if we multiply that by 6, what do we get? We get 12x plus 24y. All right, so if we subtract off 4 times 3 in the second column, so we have, let's say, 4 times 3 is, if we subtract it off, negative 12. And then if we have 4 times 6, or negative 4 times 6, is negative 24. Yeah, man, sorry about that. 3, 6 times a negative 4. What we get is 12x plus 24y. negatives, I guess they should be. So what we have is that if we try to solve for this, the x's cancel out, but the y's cancel out either. It's 2. So we cannot solve for any x's or y's. All right, so that's easy enough. All right, so let me insert a page. If we have a 3 by 3 matrix, let's say we have a 3 by 3 matrix. I'm just going to do this real quick. There's no sense in doing it by hand when Excel or MATLAB can do the work for us. I just want to show you. If we have a 3 by 3, what we do is we'll take a column or a row, and we take the maybe the first row and first column and get rid of this information and take the determinant in here. So what we're going to have is it's going to be 2 times the determinant in here. And so that's 24 minus 0, 2 times 24. All right, and then we take the second row, our first row, second column, and what we're going to do here is eliminate the first row, and we're going to take the determinant of these two things. But we alternate signs. So this was a plus 2. Now I'm going to have a minus this 4 times the determinant of 1 times 8, which is 8, minus 2 times 10, which is 20. So what is that? That's negative 12. And then I have 0, so I get rid of that column, and I take the determinant of this thing. 0 minus 6, well, 0 doesn't really matter. So when all is said and done, this is 48 minus, it should be a negative 12, minus a minus 48. So the determinant of this will be 96. All right, so in Excel, I have my little matrix right here, and the way we find the matrix in Excel is the mdeterm matrix. So I type in mdeterm, highlight all this junk in there, Control Shift Enter, and it's 96. All right, I don't know. What do we do? I guess we want to solve for this, and I tried to find a determinant of this C matrix. It's 1230, so it's invertible. All right, so now what this algorithm looks at is we have a case where we start off with this 2 by 2, and then we break it down into areas. So if we write this out as a 4 by 4, let's make it a negative 1, 0, 0, 0, 1, 2, 3, and then I have the same values as I have in the first time, 4, 2, 4, 0, 1, 3, 10, and 2, 0, 8. If I look at this matrix, if I take make it the determinant. Well, what I do is I know the determinant of this thing right here. So I take my value right there, which is going to be the negative 1. Let's see what I can do here. We have the negative 1 plus times negative 1 times the determinant in here. And well, we found the determinant in there is 96. Then we take minus 0 times the determinant of that junk, which is, who cares, it's multiplied by 0, plus this 0 times the determinant of these two things in that column. Who cares, because it's multiplied by 0. And we take this times the determinant of that area in here. Who cares what it is, because it's multiplied by 0. So the determinant of this bigger thing is going to be negative 96, which is what we found when we used our mdeterm function in Excel. All right, so we looked at determinants of 2 by 2s, and we can look at inverses of 2 by 2s. So 2, 3, 3, 4. So the quick rule of thumb is that we swap the diagonals and change signs in the off diagonals and divide through by the determinant. So if we take the inverse of this, it's going to be swap these two dudes, 4 and 2, change the signs on those, negative 3 and negative 3, and divide through by the determinant. So what do we have here? We have 8 minus 9. So that's negative 1. So our inverse is negative 4, 3, 3, negative 2. Oh man, we get the same answer. So cool, we got it. Everything's cool. And there's algorithms for 3 by 3 matrices, 4 by 4, 12 by 12. It just gets redundant or monotonous to do by hand. That's why we love Excel. We love our R. So we'll look at some applications in the last video.